So now we are ready to check that this is really a monad, that the monadic laws are satisfied, right? So the monadic laws for this, we have to be able to combine mu with eta, right? So monadic laws, if you remember, are just this. Unit law. So if you multiply unit by something, you get this something. So this is equal to a straight line, right? And there is the left unit law, and then there is the associativity law, which says if you multiply things first on the left and then on the right, it's the same as first on the right and then on the left, right? Associativity. Now we have to redraw these diagrams using stripes, okay? So, and show that this is really true. So let's redraw the first diagram using stripes. So it goes like this. Okay, weird thing, right? But this is our eta, right? And this is our epsilon, and this is our mu, right? So our mu was, okay, so what is this? This is R, L, R, L. So L goes into R, and comes back as L, right? So now if you squint and look at these stripes, okay, they form exactly this diagram, right? This is our mu, okay, this is our mu, this is our eta, okay? And now, so look at this part. This is a snake, okay? Goes from L to epsilon to eta back to L. Which one is this? It's this one. Goes from L through epsilon, eta, and L, okay? So using the snake identity, I can pull this, right? And get rid of this bump here. So this will, if I get rid of this bump, you know, I get this stripe. I straighten this line, and I just get a straight stripe, okay? So that's this unit law, huh? So the unit law follows from snake identity. What about this law? Well, this law follows, this law actually follows sort of like, well, we have to draw all these double lines, right? So it will be this, and this, and this, right? Okay. So this is one mu here, and this is the second mu here. That's the left diagram. And the right diagram is this, and maybe this. Okay. So put the dots here, right? So these are our epsilons. Epsilons are used to form mu, right? Co-unit gives us multiplication. So, well, as you can see, these diagrams are equivalent, right? I don't have to do anything. I don't even need snake identities. Why are they equivalent? Because of the interchange law, right? I can move things up and down because you've seen an interchange law, right? Interchange law tells us that we can move these dots up and down, And as long as we don't cross the lines, you know, it's the same. So this just follows from interchange law. Okay. Now, of course, there is this other combination. You know, this is R after L. R after L is a monad, right? You can show exactly like the reverse of this, or the dual of this, if you take L after R. L after R will go the other way, right? And it will generate a comonad. Okay, if you remember what a comonad. If you don't, then that's fine. I mean, a comonad is just like the opposite of a monad, a dual of a monad, right? So we get both a monad and a comonad, depending on in which direction we'll compose the two adjoint functors. So every time you have an adjunction, you get a monad and a comonad. Okay? And now the interesting thing is, the mathematicians ask themselves, well, is the opposite true? Like if I have a monad, can this monad be obtained from an adjunction? Or are there more monads than adjunctions? Right? And the answer is, surprisingly, not only that for every monad there is an adjunction, and same is true about comonads. For every comonad there is an adjunction. But actually for every monad there are many adjunctions, not just one, many adjunctions that generate the same monad. So there are pairs of functors, lots of pairs of functors that generate the same monad. And you can see that we have like, if you start with a monad, what are the degrees of freedom that you can have? Well, first of all, a monad is just an endofunctor. So you start with a single category, C, right? And if you want to create an adjunction that will correspond to this monad, well, you have to come up with a whole new category, D, on the left, right? Plus, you have to come up with these two functors, left and right, okay? So you have a lot of choices of categories that you can put on the left. So it makes sense, sort of, that there would be lots of adjunctions that generate the same monad. So I will show you one example of adjunction that generates a monad. So there's like, in fact, these adjunctions, because adjunctions can also be composed, right? I'm not going to go into composing adjunctions, but it's sort of, you know, you can easily figure out that if you have two adjunctions that go from category C to D and then from D to E, you know, that you can combine them because you can combine functors, right? And if they are adjoint, then the combined functor will also be adjoint. You can generate a unit and co-unit for them and so on. So this is sort of like an easy exercise to show that they can be composed. And because these adjunctions can be composed, then they actually form a category. So there's a whole category of adjunctions. And in this category of adjunctions corresponding to the same monad, so you start with a monad, you can create a category of adjunctions that generate this monad, and in this category of adjunctions, you have an initial object and a terminal object. And the initial object corresponds to a category that's called the Eilenberg-Mork category. Eilenberg-Mork category. So let me see what I can erase here. Let me see. I'll erase this. We can always redraw these diagrams from memory because this is like a nice notation. But let me. I think that's how you spell it. So Eilenberg-Mork category and the adjunction related to it is the initial object in this category of adjunctions, and the terminal object is called the Kleisli category. And if you remember from like years ago, I talked about the Kleisli category. It's also an important category. But I'll concentrate on the Eilenberg-Moore category. Okay? So what should I erase? Let me erase this. Okay. So the idea, I don't know what the intuition is really. Why is Eilenberg-Moore category the right category to get this adjunction that would generate a monad? In a sense, it's Eilenberg-Moore category is a category of algebras. And algebras are sort of dual to monads, right? If you think of a monad as something that, well, it's an endofunctor, so it's like a container that can contain stuff, right? But in a more narrow way, you can say a monad contains variables. So a monad can be used to construct expressions or terms, right? Whereas algebra takes a term and evaluates it. Okay, so let's talk about algebras. Algebras for a given functor. So you start with an endofunctor, okay? And this is a nice connection because a monad is an endofunctor as well, okay? And algebras are always start with an endofunctor. So endofunctor is this thing that lets you write an expression, right? So you have some functor f, endofunctor f, and you pick a particular object. And this is important. I'll be stressing this a few times at least, okay, or maybe a lot of times, that you pick a particular object, okay? So an algebra is not a polymorphic thing, okay? You pick a particular object, A, and you pick a particular morphism, I'll call it sigma, that goes from FA to A, okay? Not a polymorphic object, not a natural transformation, because we picked an A. So if you think of an algebra, let's say for a list functor, right? So you would pick an object, let's say int. Well, you get a list of int. FA is a list of int. And this sigma, which is called a structured map, or for us programmers, let's call it an evaluator. Because it evaluates this expression that I formed using my functor. For instance, I created an expression that's a list of integers. This tells me how to evaluate down to a single integer. Okay? There can be many such functions that take a list of integers and give me an integer. It could take, like, you know, maybe the first element of the list. And then you ask, well, what if the list is empty? Well, if it's empty, then return 0. Okay? Remember, it doesn't have to be polymorphic, it doesn't have to be continuous, it doesn't have to be this. There is no condition for the algebra. Just return an int. If you have a list of int, return me an int. How you do it, whatever way you want, right? So this is an algebra. For a given functor, this is called a carrier for the algebra. This object that you picked. So if you picked an integer, you know, that's integer is your carrier. Carrier type for your algebra. And this is your evaluator. Now these algebras also form a category, interestingly, right? What does it mean? Well, we have to have objects and morphisms, right? So objects in the category of algebras are algebras. So you pick, to pick an object in the category of algebras, you have to pick an object in the original category C, right? Your carrier, and you pick a morphism. And for every object, you might have many morphisms. For some objects, you may have no morphisms. Like, you know, like if this is a void type, then there are no morphisms other than void to void, right? But now, what are the morphisms between these algebras? So a morphism between algebras, two algebras. So let's say we have an algebra A and sigma, and another algebra that has some object B, and let's call it lambda, right? So if we want to map this to this, well, then we have to map the objects, right? So we'll have a morphism that goes from A to B. That's our starting point, right? So a morphism between these two algebras better be a morphism that maps A to B. But that's not good enough, because like we want to preserve some kind of structure. An algebra is a structure. It tells us how to evaluate stuff, right? So this algebra tells us how to evaluate stuff, and this algebra tells us how to evaluate stuff. And this tells us how to move from one algebra to another algebra. So it better be true that if you first evaluate and then map, it should be the same as first mapping and then evaluating, right? That means what preservation of structure means, that it doesn't matter whether you first map and then do something, or do something and then map. So what it means is that, let me draw a diagram for this. Not a string diagram, just a regular diagram, right? So we have this morphism from A to B, right? And an algebra, sigma, goes from FA to A, and the other algebra, lambda, goes from FB to B, right? Now, what does it mean? So evaluate first and then map. That's this path, right? Evaluate using sigma and then map using F. What does it mean to first map and then evaluate? Well, mapping from FA to FB means, but F is a functor, right? F is a functor, so I can lift F, right? I can F map using Haskell terminology. I can F map F. So I can take an expression of A's and map it to an expression of B's using a lifted F, right? So if this is a list of A's and this is a list of B's, you know, I can always convert a list of A's to a list of B's by F mapping this function, right? So a list will be like our standard example, right? But it doesn't have to. It could be a maybe, it could be a tree, could be like an expression tree, you know. It's like you can have a grammar with an expression tree and leaves that are, you know, of type A and so on. So preservation of structure means that this diagram commutes. So now we can define this category of algebras, right? These are objects, the algebras, and morphisms are these morphisms from the original category C that satisfy this condition. So not every morphism from A to B is good. Only those that satisfy this condition, okay? So it will be a subset of morphisms from C that preserve the algebra. So this is a very important thing. Let me rewrite it actually as lambda after FF equals F after sigma. All right? That's our condition. Okay? Okay. So that's a category of algebras that is called alg f for a given functor f. Now, going back to what I was talking about before, I was talking about monads, right? So a monad is also an endofunctor. So because it's an endofunctor, we can define algebras for this monad, right? So algebras for the monad would just be the same algebras, except that instead of f, we would put a t here, just a different letter. But now we know that this is a special endofunctor that has eta and mu, unit and multiplication, right? So now we have a way of constructing these expressions using the monad. And in particular, we can construct a trivial expression using unit, right? So a unit of the monad will give us a trivial expression in which we take a value of some type, right, and lift it to a monadic value, right? So like, again, going using this example of a list monad, right? For a list monad, unit is just taking a singleton list, right? So give me a value of some type A, I'll give you a singleton list of A with this value in it, right? So I have lots of possible lists, right? Starting with an empty list, but this is a particular type of list that is a singleton, right? And unit just creates the singleton. So now I have a way of taking a value and making an expression by applying the unit, right? Now I also have an algebra. Now an algebra will work only for a particular type A. Like unit is now let me stress this again. Unit of a monad is a natural transformation, so it's polymorphic. It will work for any A. But now I'm picking a particular algebra. I'm saying my A is fixed. Let's say an int, right? So a unit of my monad, list monad, will take this value that's an int, you know, let's say 42, right? And we'll create a singleton list that contains 42. Now I have also an algebra that operates, a list algebra, right? That tells me how to evaluate this stuff. So how should it evaluate this singleton list that contains 42?
Give you 42 back, for instance.
It should give me 42 back, right? I mean, if it doesn't give me 42 back, I mean, it doesn't have to. I mean, nobody forces an algebra to give me back 42, right? It can say like, sorry, I only have 40. I already spent 2, right? Or I spent 40 and this is 2, right? So it doesn't, nobody forces it. So we have to impose these additional conditions if we want to have a well-behaved algebra that respects my monad, okay? Like a really honest algebra that if you give it 42, it will give you 42 back. It won't cheat, okay? So if you want to have an honest algebra, which is compatible with the monad, you want to impose this condition, you know? So like sigma after unit should be identity, right? Okay, I can draw a diagram. So I start with A, right? Eta give me TA, and sigma evaluates TA to A, right? And now I want these two to be equal. So that's a condition. Okay. What's the other condition? The other condition is we also have this multiplication, right? So we want this multiplication in the monad to be compatible with evaluation. Now, unit and evaluation went opposite ways, right? But evaluation and multiplication go the same way. But you have to start with something that has more structure. So like if you take TTA, right? Then there are two ways of evaluating TTA. One is you can first apply mu or flat map, right, to get TA. And then you can evaluate TA using sigma to get A, right? Or you can say, I can lift sigma, so I can apply T sigma to evaluate the inner expression here, right? Because this is like an expression whose leaves are expressions. So I can evaluate the inner expressions first, and I will get something of type TA. And then I can use sigma to evaluate it, right? There are two ways of going about it. If this is a list of lists, right? Going again with the same example, I can first use mu to concatenate a list of lists, and I get a single list. And then I can use sigma to evaluate it. Or I can say, I'm going to evaluate all these sublists separately using T sigma. So I apply sigma to every sublist, right? And what I get is a smaller list. And then I can evaluate this smaller list using sigma, and I should get the same. Okay? So these are the coherence conditions that say these algebras that satisfy these coherence conditions are called the monad algebras. And these monad algebras form the Eilenberg-Moore category. Okay? And next time we'll talk about Eilenberg-Moore category and the adjunction that gives us back our monad. Okay?